Hello, welcome everyone, and thanks joining us on Apex Meetup. We have some couple of announcements. So Apex went top level project last week. So we had a bit of a celebration. You can see all the decorations behind you, and the also the meetups are growing. Strength has now crossed 8,000. Today we have two talks. One is by Chandni. It's about the HDFS input and output operators on Apex and how they're fault tolerant. And the second talk is by Sandesh, and it's about the Yahoo benchmarking application on Apex. So with that, ask Chandni to come up here. Chandni was a Tolerant employee, and she worked on the HDFS input and output operators, which are one of the widely used operators, especially in the batch use cases. And I'll turn it over to her.
Hi, I'm Chandni Singh. I'm a committer of Apache Apex, and today we'll be discussing some quite frequently used input and output operator, file input operators in the Apache Apex Malhar library. The focus of today's talk would be on fault tolerant, how these operators are made fault tolerant. So before we get into the details of the operator, let's okay. The animation is a little screwed up. Okay, so let's look at some of the main concepts in the Apache Apex platform, which we will refer to frequently. The main concept is the windowing in Apex. So O'Reilly describes window as a finite piece of a data set along temporal boundaries. In Apache Apex, each such window is assigned an ID, and using this window ID, an operator developer can make any operator fault tolerant. Also, when we write an operator, it is provided with hooks to know which window ID it is on. These are like begin window, you get a window ID. When you checkpoint, you get a window ID. So with these window IDs, you can actually make your operators fault tolerant. You can imagine window ID to be associated with every tuple in the application and even with every operator. This was a simple tag which has 3 operators in it. The tuples are flowing between these operators, and there's a notion of window ID with each tuple and as well as the operator. We look at other examples, it will be clear then. So moving on to the solutions which help reading from files. There are 2 solutions in Malhar library. One is the AbstractFileInputOperator. This is for reading approximately equal sized files. There are also extensions of this input operator which provide out of the box support for reading text, Parquet and Avro. Then the other solution, which is a combination of 2 logical operators, FileSplitterinput and AbstractFSBlockReader. These solutions help reading different sized files, and it helps parallelizing read on a single file. So the first operator that we'll discuss today, the file input operator. The function is very simple. This operator is provided with a folder or a set of folders, and it scans these folders periodically to discover new files. As and when it discovers a file, it opens it and passes records from it. It has to do all this in a fault-tolerant way, and it is scalable as well. So as I mentioned, the focus today is on fault tolerance. We'll see the fault tolerance part in detail. First we'll see what fault tolerance means here. Any Apex application is a distributed application. It has multiple operators that runs in the cluster. An Apex application is fault tolerant if it can sustain a loss. In the context of the input operator here, fault tolerant, it will be fault tolerant if a record is never lost. A record should always be associated with only one window ID irrespective of the failures. And if a window is replayed, then all the records associated with that window will be replayed. So let's see this with an example. Okay. In this example, there is the file input operator, which is which reads from file A, and it emits out the contents of file A. So what happens is that it reads line 0 and line 1, and these tuples are associated with window 0. Then it reads line 2 and line 3, which are associated with window 1. This is a very simple use case where we assume that the state is checkpointed every window. So now what will happen? What happens here is that window 0 gets committed, but just after the end of window 1, the operator fails, and window 1 is failed to checkpoint. When there's a failure in just after window 1 gets ended, but it fails to checkpoint. So then the operator will be redeployed in a different container. So now when it comes up in a different container, it needs to start processing tuples from the beginning of window 1. If what it does is it starts reading file A from the beginning and emits line 0 and line 1 in window 1, then that is not the right behavior. That's the incorrect behavior. The correct behavior would be that it remembers what was the state after window 0, and it starts reading file A from line 2 and emits tuples line 2 and line 3 in window 1. So the abstract file input operator that we have in our library exhibits this behavior, and in order for it to be fault tolerant, it needs support from the platform and some other some other utilities. So what it needs from the platform is automatic checkpointing of the state of every operator in the tag, which the platform provides. Also, it relies on the restoration of a failed operator in another container. This operator is an input operator, so this support is not sufficient. It needs to replay data of a window which it had finished in the previous run, and for that it uses a utility called Window Data Manager, which is present in the Malha library. Window Data Manager helps saving incremental state of the operator. This state is actually read when the operator is recovering and replaying window, and this state is used to replay the tuples of a previously completed window. So for this operator, the checkpointed state would be a set of processed files and the last open file and the offset till which that file was read. The incremental state here is list of all the files that the operator read from the start offset to end offset in that particular window. So for example, assuming that checkpointing happens every 60th window, at the end of 60th window, the operator state is checkpointed, which consists of file 1 and file 2 as processed files, and then it also records file 3 as the last open file which was read till offset 50. The incremental state, there will be that file 2 was read from offset 50 to offset 100, and file 3 was read from offset 0 to 50. The next window, which is Windows 60, there is no checkpointed state there. There is only incremental state there. It will record that file 3 was read from offset 50 to 100 and file 4 from offset 0 to 50, and so on for 61. Now, if the operator failed in between Windows 62, it will be restored with the checkpointed state of Windows 59. So it will know that it had already processed file 1 and file 2, and it will know that it had processed file 3 partly till offset 50. Um, when after the restoration, when it starts processing Windows 60, it will know that it had completed Windows 60 in the previous run, so um, it will use the incremental state information and open file 3, read it from offset 50 to offset 100, and file 4 from 0 to 50, and it will do the same for the Windows 61. In Windows 62, where there is no incremental state, the operator will just resume its normal processing. So this is how this operator is made fault tolerant in Apex.
So Chandni, there's a question online.
Okay.
Can you take like 30 seconds and explain Windows concept?
Oh, sure.
Thanks.
So, well, windows are basically in the context of Apex windows. We have unbounded data coming in. We divide that unbounded data into discrete sets, and each such set is a window. So it doesn't mean that that the tuples which are flowing through the application, they are batched, but we just tag each tuple with a window ID. So that basically is a window. Okay.
So the incremental state is also persisted in the same place where the checkpoint are persisted in HDFS by default.
So it is persisted in HDFS by default. The folder where it is persisted is configurable. It is by default it's present under the application path.
Okay.
Yeah.
And it persists after processing.
So it is persisted at the end of the window, application window.
So what's the advantage of separately resolving the incremental and the checkpoint? Would have combined
There is the advantage. The advantage is incremental checkpoint. It will help the input operator to replay a window which only it had finished, but other operators downstream wouldn't have finished those windows. So that is what is contained in the incremental state. There are some use cases where you wouldn't want to do this, because saving incremental state every application window is a costly thing. So there are times when an application can take let's say can take out of order tuples, handle out of order tuples because the tuple itself has an ID, and some operator down the application some operator downstream can handle that. So in that case, you wouldn't want to save this incremental state. Then you'll just rely on the checkpointed state.
The events within the window will be still replayed, and you have to take care of that. If you don't want duplicates or want to use the exact one semantics, then you have to write application logic to provide it.
Yes, the operator has to, and this is basically done for the input operators. When incremental state is always needed most in the input operators, because they need some way of replaying the data, which I'll cover in intermediate operators. The platform itself does it.
So, do use the mic when you have questions. There are 3 more questions online.
Okay.
How is the window ID generated?
The input operator has a window generator in it. It creates these window IDs. Oh, I'm sorry. So the question was, how are the window IDs generated? And the answer to that is that there's a window generator in the input operator. It generates window IDs.
Like, what makes it unique? Is it based on a content?
Window IDs are basically time-based, so they keep on monotonically increasing with time.
And how is the window decided?
So window will be it's a number. It's like a train that if you're reading, let's say from Kafka, you read, let's say in your logic you read around 10. You read 10 tuples, and after that you stop, and then you continue with the next window. So it's like that.
Configurable, right?
Yes.
Based on size? Based on time.
Based on time, yeah.
Sunny, keep repeating questions because it will not get recorded otherwise.
Okay.
Or force them to produce online.
I see.
So the 3 questions now online. Let's go on. Check on. Okay. So the first question here is, how is it in the third diagram in the previous slide is the correct behavior? There is no line 1 read between begin 1 and end 1.
Oh, I mentioned that window 0 gets committed. Window 0 being committed means that all the operators in the DAG have seen that window and have processed all the tuples of that window. So that window doesn't need to be replayed.
Okay, next question is, and you could probably cover it later. Next question is it a sliding window? And again, is backed up randomly?
It's not. Right in here we support sliding window, but this is not an example of sliding window. This is a tumbling window. And I think we have back pressure in the platform.
Okay, thanks.
So yeah, that was about the fault tolerance. Now scalability. The operator is partitionable. By default, it is manually partitionable. When there are different partitions, each partition reads different subset of files. Files are distributed between partitions based on their hash. So in this example, if there are 4 files and 2 partitions, partition 1 will read data of file 1 and file 3, and partition 2 will read data of file 2 and file 4. The number of partitions can change at runtime by just changing a property. There are, for advanced use cases, subclasses can override the directory scanner, which is actually a property of FileInputOperator, to customize behavior such as having each partition scan a different directory. There's also support for auto scalability, which is provided in AbstractFileInputOperator, which is also present in the library. So there are a few implementations of the file input operator. Actually, just one implementation in Malaha library called line-by-line file input operator. This operator reads lines from files and emits line as a string onto its output port. To create a custom implementation, you need to extend AbstractFileInputOperator and provide implementation for 2 abstract methods, read entity and emit. Typically, emit will just emit the record on the output port. So now the other solution that we have for reading is FileSplitterinput and AbstractFSBlockReader. In this solution, the task of discovering files and reading them is separated into different logical operators. The file splitter discovers files asynchronously and creates task descriptions which are called file block metadata. The block readers, which are downstream to file splitter, they use this file block metadata to read a particular block of file. So in this, there's a small example. There's a file splitter input, and then there are 3 block readers. File splitter input will discover files and create file block metadata tuples. Block reader will act on this. File block metadata, and it will open a particular block of the file and create records from it. This solution is fault tolerant as well. It can parallelize reading on a single file, and it's auto scalable. So in this solution too, the file splitter input and the abstract block reader, they both depend on the platform support for checkpointing state and redeployment. File splitter input is again an input operator, and it is very much like the abstract file input operator. So it uses the window data manager utility to replay tuples of a completed window. Here, the block reader is an intermediate operator, and so it doesn't need any additional support. It just leverages the platform support for fault tolerance. So what it specifically relies on is the upstream operator buffer server to replay the tuples of a given window. So a buffer server is a buffer associated with each output port of an operator, which holds tuples emitted by that port. Let's see with a simple example. In this, there's a file splitter which discovered file A and created 2 file block metadata tuples from it. There are 2 block reader partitions. Partition 1, which is the top one, starts reading file A from offset 0 up to length 50. Partition 2 opens file A from offset 50 up to length 100. The first partition completes Windows 0 by emitting line 0 and line 1. The second partition, however, just emits line 2 and then it fails. So in this case, block reader, the second partition of block reader will be redeployed in another container. The first, the other operators in this application will continue processing as it is. So when the second partition is redeployed, it will start the processing from the beginning of Windows 0. So it requests the upstream buffer server to replay data from Windows 0, and once that data is replayed, it will open file A, start reading from offset 50 up to length 100, and emit line 2 and line 3 and complete Windows 0. So this is how fault tolerance is achieved.
There's an online question which was repeated.
Okay.
So how are the partition sizes decided, or what is the basis of file split?
So the question is, what's the basis of file split? It's again a configurable property. By default, this property this is assigned as the default HDFS block size, which I think is 64 MB, but it can be configured.
So in this example, you're assuming that your object 50 corresponds to line 2.
Yeah, this is just to illustrate how fault tolerance work. I mean, I'm assuming that line 0 and line 1 are 50 bytes. That's very simple illustration. Okay, so moving on. Scalability in this case, file splitter input is a very simple operator. It doesn't open any file. It just from the file metadata, metadata, which is length of the file, it creates a block, file block metadata. So it doesn't take much resources, so that doesn't need to be partitioned. Block reader does the actual work of reading files and is also scalable. It is statically scalable as well as auto-scalable. So here some important configurations which are related to partitioning are minimum and maximum number of partitions. Also the frequency of repartition is controlled by a time interval property. The operator decides to scale up or down based on the pending file block metadata in the input port queue. So here, in the simple DAG, there is a file splitter input and there were two block reader partitions. Both of these partitions had two file block metadata queue in the input port. So now, based on this operator will try to reduce this backlog to 0. So it will create two more partitions of block reader, and all these partitions will be deployed, and they all get one file block metadata, and then they start they read the corresponding block in the file and emit records from it. Once after a certain period, when there are no more pending file block metadata, it will scale down to 2. This feature is still in beta. We have just tested it in isolation, so we need to test it more. Okay, so moving on.
So, a quick question. Since Apex is built over HDFS and all files internally split according to HDFS block, what features being used to do file splits? It will not be expensive.
So, since can you repeat the question?
Since Apex is built over HDFS and all files internally split according to HDFS block, what feature is being leveraged while using file splitter?
Well, Apex is a platform which is used to write very generic applications. So here, the notion of where each HDFS block resides is not used. The block metadata is constructed just based on the file size, so it doesn't use that information.
Also, the underlying file system might not be HDFS.
Yeah, also, exactly. The underlying file system may not be HDFS. Does that answer? Okay. Okay, so implementations of file splitter input and AbstractFS block reader. File splitter input is a concrete operator. You can use it just out of the box. But some default behavior can be overwritten, and these behavior is respect to how you want to scan a directory. We have couple of block readers in the library. The first one is a concrete one, which is slice reader. Here, the record is a slice, and a slice is nothing but a wrapper around a byte array. There are AbstractFS line reader and AbstractFS reader headline reader. Here, the record that it emits is a line. We have two implementations of these because these implementation differ how they handle a record which is split split between adjacent blocks. To create a custom block reader, you can extend the AbstractFS block reader in the library, and you need to provide a reader context to it, and provide an implementation for converting bytes into the record that you are going to emit. So now we come to the operator which writes two files. The function of this operator is also very simple. It persists data to a single file, or it can persist data to multiple files. The file it persists to is derived from the tuple, or there is also an implementation in the library which writes to just a single file. It has some optional features added. Automatic rotation, which is based on either the file size or the window count. Window count because that gives a notion of time. Then there's a feature for compression or encryption of data. This is also fault tolerant, and it's scalable as long as different partitions write to different files. Subclasses can achieve this by appending the operator ID to the file name. So in the context of file output operator, let's see how fault tolerance is achieved. What is fault tolerance actually? This operator is fault tolerant only if it persists every tuple exactly once, which entails that a record is never missed and a record is never duplicated. We have an example application that persists data exactly once and uses a concrete implementation of this operator, which is present here. We'll not go there right now. We'll see a simple example. So in this example, there's a file output operator which is writing to file A, and it's just an extension of the previous example. So here line 0 and line 1 tuples belong to window 0, and line 2 and line 3 belong to window 1. So this operator completes window 0, and then it appends line 2 and line 3 to file A, and just after flushing it crashes. So now when it comes back up again in a different container, it had already completed window 0. So only the tuples from window 1 will be replayed to it. So if it doesn't do anything, and again it writes line 2, it appends line 2 and line 3 to file A, there'll be duplicate records in line 2 and line in the file. So this is incorrect. This is not fault tolerant. The correct behavior here would be first to truncate file A to the size, truncate file A to a size which was after Windows 0. So for example, when it's redeployed, it truncates file A to contain only line 0 and line 1. Now when data from window 1 is replayed, it will append line 2 and line 3 to it, and this is the correct behavior. So the operator that we have in library exhibits this behavior.
One more question here. And can you repeat it? What constrains the upper limit on the number of splits? The number of cores or number of or the memory, or both? What constrains the upper limit on the number of splits? The number of cores or memory or both?
I don't understand the question.
What constrains the number of partitions?
Number of partitions of the output operator. Well, you can have as many output operator. I mean, that depends on the cluster, on the HDFS cluster, so number of cores. Yeah. You have a question? Okay, so yeah, so this is how the operator is fault tolerant. Well, No, I mean let's look at how the operator is made for Tolerant. So to write exactly once, the operator first of all assumes idempotent processing. In this case, idempotent processing actually means that a tuple, if a tuple is associated with a particular window, it's always associated with that window. So for example, tuple 1 is, if it belongs to window 1, it will always belong to window 1. It will never belong to any other window. And then it also relies on the checkpointing done by the platform. The checkpointed state here will consist of size of each file the operator has written so far. It has additional intelligence in the built-in, which helps it to truncate files to the size saved in the restoration checkpoint, which is the example we just saw. But I mean, just to truncate the files is simple, but when we are writing to HDFS, we have more problems. The other big problem that we have seen is dangling lease issues in HDFS. Let me explain what a dangling lease is. Um, an instance of abstract file output operator, when it writes to a file, let's say file A, it will first acquire the lease of that file from the name node. So when it acquires the lease of the file, it can start writing then. However, if it crashes, if the operator crashes, before closing the file, the name node will still hold that lease, will still see that lease to be open. Now, if this operator instance is restored in a different container, and it wants to write to the same file again, it may not be able to acquire the lease of the same file because the previous lease is still active. So we handle all this in the solution we have. We always write data to temporary files. The temporary files are renamed to the actual file when the file is finalized. And by finalization, we mean that the file will never be opened again to write. So this user can choose when the file gets finalized. It's handled automatically when rotation is enabled. Okay, so there's no implementation of concrete implementation in the library because we leave the file name open, and we need to get bytes from the tuple, and that's very specific to a concrete implementation. So if someone has to write a custom implementation, they will just extend the abstract file output operator in the library, provide an implementation for file name, provide an implementation for get bytes, and in order to avoid explicit finalization, you can set them. You can enable rotation, which is here done by setting a max length and the rotation windows. So that's it. Thank you, and would like to acknowledge these folks which helped me to prepare this presentation, and the organizers and the Apache Apex community. Well, I can take questions now.
For the file output operator,
yeah.
Is it safe to assume that everything that is coming in, it's only in the append mode? Because when you're truncating, the assumption that it's only appended at the end. But if it was inserted in the middle of the file, then the truncation will not work.
Well, the file output operator that we have, it always opens a file in create mode, not append mode. So why it does that is because we always write to a temporary file. So now if you have a temporary file and and you fail and you have to write the data to another temporary file, we first copy the contents of that temporary file to the new temporary file and then start. And this we do all that to avoid the least exceptions.
So the by truncation you really mean replacing the
yes. Yeah.
It's not really
No. Yeah, it's an effective truncation, not yeah.
Is there any other abstract operator or interface which I can implement to mimic the same behavior of AbstractFileOutputOperator to maybe a database? Or
we have a lot of abstract implementations for persisting in databases like JDBC. I believe some other Cassandra.
But especially the one that helped me mimics the write only one record.
All the database implementation that we have in Mulha library are for write only. This here for writing exactly once, we need to do this effective truncation. But for Cassandra or JDBC, we rely on a different mechanism. For JDBC, for example, we rely on transactions to provide exactly once.
So the library gives me
yes. So all this, all for any database, not all the database, but most commonly used database, we have these implementations where fault tolerance exactly once behavior is already provided.
So in this architecture, right? So if I have to do a transformation, I'm reading the files specifically for your file input operation. If I have to do a transformation, where do you suggest us to put the transformation things, and are there any libraries that we use for transformation, or we have to do like Java code within your emit operation, emit function?
Well, you can let me go back to file input operator. So yeah, here you can do a transformation in the, you can override the emit method and do any transformation there. If it is a bulky transformation, we would suggest to do it in a different logical operator. I mean, it depends on you wherever you would like to do that.
So for the bulky transformation, right? This is the question. You are sort of storing the intermediate checkpoints after the main checkpoint. You're storing the intermediate. So if I do a transformation here for one or two lines, which in the intermediate stage is already transformed, would you store that and write it directly, or would you do the transformation again?
So here, what we in the incremental checkpoint, what we save is some metadata. So metadata of what was read from the file. So if that window is replayed, the same data will be read from the file again, and your transformations will be reapplied again.
Any other questions? Okay. Thank you, Charlie.
Thank you.
The next speaker is Sandesh. He's going to talk about the results of running the Yahoo Streaming benchmarks on Apex. Sandesh is an engineer at Tolerant, and he works on Apex and application.
Good evening, everybody. Thanks for waiting for my talk, myself. So today it's about extending the Yahoo benchmark. So to give you background on what it is, So now in the market we have multiple streaming engines. Right? So the Yahoo guys said, okay, let us. So Yahoo guys said, okay, let us benchmark a few of them. Right? So what they compared was they compared Storm, Flink, and Spark streaming. So I have the reference. You guys can go and take a look like what they have done. Right? So then, so the data artisans, the company banned Flink. So they extended the benchmark and they compared Flink and Storm. And we said, okay, the benchmark comparisons cannot be complete because none of them have compared with Apex, because Apex may be young in open source years, so open source last year, but it's in development since 2012, and it's in production in many big companies. So that's why we really said, okay, we need to do that comparison and present it. So essentially, this is the benchmark. It's a simple advertisement applications, and you want to know like how successful your campaign is, how many hits your campaign is getting, right? So you're reading from Kafka, and there is a JSON string. You deserialize it, and you filter unnecessary ads, and you do few of the operations. So if I represent this same text in a diagram, this is what it will look like. You are reading from Kafka and deserializing it, filter, and ultimately you are storing it in Redis for a query purpose. So then next I want to talk about few setup. I don't want to spend much time here. So the message size is approximately 200 bytes, and this is a sample message that that gets sent through Kafka. User ID, page ID, ad ID, and ad type, and all this. That's the type of the message. So next is the Apex applications. So how your applications gets built, right? So if I go back to the diagram, so this is how you develop your Apex applications. So every block you consider it as an operator, and you connect the streams between them. That's all you do, and lot of scalability, fault tolerance, many things are built into the platform, so it makes it really easy for you. So if I go back to the code now, so now you can see that, so I'm creating the operators first, Kafka, deserialize, filter, so the same as in my diagram, and I'm connecting the streams. I'm setting few properties. I'll explain about them later, but that's essentially what you do. And we are also working on high-level APIs, but we still believe that for finer control, you will end up using this API. So now, once you develop this application, so you have to note few things. I have not mentioned how many partitions I want or anything like that. This is essentially the application, and it's open source. You can go and take a look. And now what happens when I run it is, this is what happens. So I had 8 Kafka partitions running on 4 brokers. So now, without mentioning, I have 8 instances of the Kafka input operators, right? So, and you have multiple operators, and so if I take example of the first line, right, Kafka input and the deserialize, so they can be running on the same containers, or they can be running on the different containers. Containers here is a yarn containers, right? So if they are running on different containers or the different machines, then there is a network overhead. But in Apex, what you can do is you can say that let me run them in the same container. Not only that, you can say that, okay, let me run them in the same thread. Then it just becomes like a function call. So, for that we have the terminology called container local and thread local. Container local is we run the operators as a multiple threads in a container, and thread local means it's just a function call. So just a quick note, and we have a few other features like anti-affinity, which we are not talking about here. If you require that some operators should not be together, then you can mention it as well. This is a new feature that we have introduced. Another thing is, so we take benchmarking seriously, and every release we do benchmarking of various features that we have, like container. This is one example wherein we compared the older version of the Apex for the container local with the different data size and everything. Right. So then, so the main point about this talk is to compare with Flink. So what we did was we ran the same applications with Flink and Kafka. This is the number we got. right? So with 8 partitions of Kafka, we are able to do 1.2 million. We possibly could do more in Kafka, but you need to have the skills to set up the Kafka properly, and so that I certainly didn't have. So what we did was, so we said, okay, 1.2 million doesn't sound interesting from 8 partitions. We said, okay, let us do more, right? So either I needed more servers, or I need a different way of doing it. So that's what we did was, we said, okay, now let us not use Kafka. Instead of that, let's use a generator. So now whatever the message that was coming through Kafka, so now it's essentially it's a part of the tag which gets which is generating the message. So now we are able to generate a high throughput message. So now when we do that, something interesting happened, and we are able to get to this result. So because now what happened was, now no more we are limited by a small number of data coming through. Now we are getting high throughput data, and this is the result we got. So the Apex did twice that of Flink. So the reason we think is because they have one more extra serialization overhead, which we don't, because the reason I explained container local is because of this. So we can club together, and you can avoid the deserialization, because when they are running in same container in same thread, it's just a blocking queue that you use. We have different mechanisms, but that's essentially the result we get. Now, so the next is you saw the reason we did all these things is to get the query result. Okay. No. So the Flink, yeah. No, so it didn't went down. So what happened was Apex went up. Even their performance also went up, but the Apex went up more drastically compared to the previous setup. Yeah.
Unless you are going to take the mic.
Huh? Okay. Okay. So we are simulating the situation here, right? We are simulating a situation of ads coming through. So initially, what we did was it was coming through Kafka, but we were putting into Kafka. We wrote another Apex application which was putting data into Kafka. So then, so now we have like putting into Kafka, then it is a read, right? So now we said, okay, instead of doing that, you will put that part into the application itself. So now there is no going through Kafka. So that helps us to, like, within our limited resources, helps to see more number of tuples going through. Otherwise, now we need a more Kafka servers. Now that's why we did that.
Unless you are going to cover it later,
yeah.
Feel free to ignore my question. But what kind of configuration you need to improve the performance? You just mentioned that now because Apex supports container, local, and regular port.
Yeah.
So which operator were configured to execute together in the same container or same thread?
Okay, so if I'm looking at this diagram, so the first 4 operators, so they were in the same containers. So they were running as a multiple threads in the same container, and there was a queue between them. So there is no serialization involved, right? So the tuples are just passing through as a normal queue. And the last Redis output, not to overload the Redis, we kind of had the unifier, so it unifies it. If I go back to the diagram, it will be clear, right? So now if you look at this diagram, so this is our exact physical plan. The first, the 5 operators, right, including the Redis join. So those things run as one container. So now I have 8 containers here. So each line is one container. So all those things are running parallelly in single container. Okay. Anybody has questions? Okay. So all this is good, right? So this is a benchmarking application, but what exactly the state of the art in streaming, or we want a state to be queried, right? We are putting into Redis, And the question that we asked was, okay, is this what we recommend to our customer? The answer is no. This is what this is just a benchmarking example. Okay, this is one hypothetical case, but the real power is not just in this. So the one simple thing that people say is, okay, put it into memory, just query the memory. You can have more any mechanism to query the. You can have RPC server running in your operators, which can query the state of the operators. Now we can have all the scale out and everything, but that is not useful in many cases because you can the memory may not be sufficient, or you want to have the durability in your data, right? So so what is our recommendation, right? So this is our recommendation, right? So so what has happened is the first 4 operators up to Redis join, it's the same. The next 3 operators, so they are library operators. So now the interesting thing what happens is the coding effort is really less. You are not doing much, but you are getting a lot. So what happens now the one is a dimensional computation, wherein you can define your own buckets and everything, time buckets and everything. So you can do aggregation. So then next is a store. The store is we use HDFS to store it. We have our own key value store called HDST. So the data gets stored on HDFS, and the query result can send the query to your own console. So here what I will show you is so the same thing integrated with data torrents RTS control, how the data is getting shown in the UI in the real time. I have a demo for that, right? So this system we say it's much better than Redis because now this scales with your application, and you don't need a separate system to maintain. You don't need a separate Redis cluster to maintain. You don't need a skill for Redis. You don't even have to worry. So you have the Apex skills. You just go with that, right? Single system and low operability cost, right? So I have a demo, so I'll show you the demo. I think the SSH connections are down. What's the password for this? So Pramod, the SSH password for this? Putty. I did. Sudo. Delete the UI or any of the UI. Okay. Move it to the right. That screen shared. Okay. Okay, so I'll show you the app running. Okay, so this is exactly the DAG that I showed you guys. So the event generator, filter tuples. This is a logical view of the DAG. So if I click, if you can see the numbers. Numbers are crazy, right? So numbers are high. So single instances cannot generate these many events. But if I click on the physical DAG, this is what is internally happening. So I have 8 instances of all the event generators and everything, right? So it's getting to the store, and we have the query result operator. So now then, so now interesting thing happens is this is already integrated with the UI. So if I click on that, so what you can see here is I showed you the message earlier. It had a campaign ID in some GUID, right? So for that GUID, you can see the result here on the UI, right? So it's a 10-second bucket. So you can see that on the left hand side you have all the 10-second buckets and how many times the each campaign ID has been hit. So this is just we can add any campaign IDs. So I can show you guys adding new campaign IDs. So here you can add any campaign IDs, right? So I can just type and it will suggest me the existing ones. So I can select any one of them. So the thing to note is it could be anything. It could be your cities, it could be maps, and anything, right? So here in this case it was just a grid. So that's why it is showing you the numbers. So let me select one random one. So now you can see that you have more data. And this is getting updated in real time. You don't even need a Redis or your query or anything. So, and not only that, so we are adding more widgets so that now you can visualize your data in different ways. So now the scalable application and the visualization built in. So this is what we say. This is a state-of-the-art streaming technology that we want to present.
Yeah. So in your case, was the campaign ID was the only thing in event?
No. So it's a campaign ID. There is an ad ID. So campaign ID is not sent in the event generator. Event generator sends the ad ID and a few other informations. It's click or what kind of ad it was and everything. So finally when an ad ID comes, we just do Redis lookup to see the campaign ID for that ad ID. So then there we get the campaign IDs.
Yeah, I was thinking more about like maybe think about application other than this. How can you get a different dimensions of what if I want to see data by city or then?
Yeah, so that's what you build your application. That's I showed you the dimensional computation, right? So while it can take the schema and build it according to you. So then you do all those things, and then query also you need to change the query according to that. So now the query is written for these kinds of data. Now you'll have to change the query little, but it's a library, so it's very easy for you to write.
Yeah. Like Redis, right? Redis is probably a schema you store. Do you have any support for other indexing mechanisms like Elasticsearch or something like that?
Yeah. So at the Apex, right, we have like Apex has two parts. One is core engine. So next to the library. So library is operators. So we have kind of 400 plus operators built in, right? So standard stores, we already have the operators built in. You just plug it in and you are good to go.
So the other question is regarding, so now you store everything on HDFS and then you query the HDFS, right? In the new proposed model.
Yeah.
What is the latency hit? Do you have any numbers for that?
So the latency we have not calculated, but so the overall we can, so if you look at the console can show you some latency numbers as well. So you can see the latency here.
So what would be the relative overhead that I'm paying in terms of latency to go to this new model for scaling?
It's not just about the latency, right? It's also about the operational cost. So now, say I showed you about this here, right? Now I have 8 instances, right? So now I can go to like 20, 30 instances, right? But then now you have to think about how much Redis servers you need and everything. Here you are not worrying about any of those things, right? So the operation becomes easy for you, and everything is in a single. Those stores understand the Apex stack, right? It scales along with that.
So the view what you showed, where you could pick a dimension or a particular campaign, and you could see all the relevant data.
Yeah.
But if, as an analyst, somebody wants to write a query or they don't even know what data to look for, more like a data discovery.
Yeah.
How does this platform support that?
Yeah, so we can we do have support for stripped down version of the kind of, I should not be saying it SQL query. It's not SQL query, but it's we do have support for that small query. We are enhancing that based on the demand. You can query the data.
And do you guys have any out-of-the-box drivers or connectors to that? Visualization to like Tableau, QQ, or any of that, those will be connected to this platform?
Not directly, but if we can build operators which exposes the data to them, maybe yes. But we have not built it out of the box yet. Okay. Any more questions? Okay, so that's pretty much it from my side. So last slide. Q&A we already covered, and so these are the links so that if you want to know more about the features that I talked about, so you can take a look. Dimensional computation, HDFS, or the how you query the data and everything. Slide share, yes. So we'll post these slides and videos online. Okay. Thank you, guys. Okay.
Do you have any numbers with Storm also?
Storm, Flink already did that, so we compared with the Flink. So that's kind of, we believe that it's a transitive, so that's why we didn't compare Storm. Spark streaming, right? Even the Spark streaming we didn't compare because so Spark streaming is a micro batch. We are not a micro batch, right? So we are true streaming platform. So we didn't compare with Spark streaming as well. All right. Okay. Thank you, guys. Thank you for your time.
Thanks everyone for attending the meetup. A few things on the way. We are going to publish the slides from the meetup. We are also going to post the recordings. There is going to be a YouTube video and also the GoToMeeting recording is going to be posted. Please have a look at the last slide that contains the mailing list addresses and other resources that you can look into. Please subscribe. And upcoming events, we have next week a meetup here at GE is going to present their work with Apex on, I believe it's Wednesday, right? And then we're also going to be at the Apache Big Data Con in Vancouver on Monday. I'm going to speak there. Yes, please join the community, and if you have any other questions, please contact us through the Meetup group or through the mailing list. And on the way out, if you want to fill out a feedback form, you can get yourself an Apex t-shirt also. Thanks all for coming.
How do you decide if this